Section 6. Consider the third degree polynomial, i.e. cubic, function f of x equals 12x cubed plus 13x squared minus 185x plus 114. Let's find all local x-intercepts and find all local maximum and minimum points. Alright, so problems like this are greatly assisted if you know what the basic structure of the polynomial looks like, or the function looks like. So we know, for example, if it was a second degree polynomial, we know that it looks like this, or it looks like that. But it's not second degree, it's third degree. And let me just go ahead and tell you that third degree polynomials, the rough shape is either something like this, that's supposed to be going up like that, or it's something like that. Okay, roughly. Now these things can be kind of smoothed out or exaggerated, just sort of depends. But with this in mind, if I want to find the x-intercepts, you can kind of think about like how many x-intercepts could you possibly have for something that looked like this. Well, the maximum number you could get is if all of this curvature kind of happened around the x-axis, and so that would give us 3 x-intercepts. So the highest number we could have of x-intercepts would be 3. Similarly, for local maximum and minimum, knowing what the picture looks like will tell us something about how many of these we could have. So turning points, well, we've only got 2 of them. So we have a local minimum or a local maximum and only 1 of each. Okay. So that's a little more explanation of this statement down at the bottom. Why does it say a cubic can have up to 3 x-intercepts and up to 2 turning points? Well, that's why. Okay. But anyway, back to the problem. It's a fairly straightforward question. We really just have to enter the function and get rid of this. Enter the function and graph it, and then find all these points. So I think the main issue here is just sort of having the patience to do it. And then also getting a reasonable graph. So I think first of all I'll start with a zoom standard and see if that gets me anything. Alright, that actually was pretty useful, because if you notice there were 3 lines that kind of came swooping through. Basically what this is telling me is that I need less of x and more of y. Okay, so I'm going to go from x, I'm going to go from -5 to +5, and I'm going to do zoom fit with that, and that will make my y range, that'll give me more of a y range. Aha, now look at that. Now you see how dramatically different that looks than my first picture. It's all in the window, right? Okay, so there we go. Now we can see we actually do have 3 x-intercepts. 1, 2, 3. So we'll need to find all of those, and we have our maximum there, our local maximum there, our local minimum there. This is not a local maximum, that's not our minimum, that's not a local maximum in the leftmost and rightmost corners, because the function continues to go down and go up, and we're not restricting our domain here, we're looking at the full domain. Okay, so now let's look at finding those zeros. My cursor happens to be right here, so I think I'll find this one first, which is like the middle one. So that's kind of weird, but whatever. Okay, so 0.67 is 1 intercept. So 0.67, that would be 1 intercept. Then we basically just do this 2 more times, so a total of 3 times. And so now I'm going to go find this other one over here, which is the rightmost intercept. My picture's a little crappy, but I can still work with it. So there you go. There's my rightmost intercept is 3. And I think hopefully you get the idea now. So to find the leftmost intercept, I'd need to move my cursor over here and run through the Calc 0 process again. I don't want to do that, so you can do it if to find the third one. Finding the local maximum and minimum. Honestly, that's not really anything new either there. So for like the local max, or rather I should have done local min, because I'm pretty close to the local min already. So to find that local minimum, we have to, the basic thing is we just have to remember how to do this left bound, right bound stuff. My window is really bothering me, so I'm going to change that. I need more room underneath, and now I have it. Okay. So I want to find the local min. And it's over here. Left bound, right bound, guess. And my local min is 1.93, comma, negative 108. Or sorry, 1.94. I'm sorry, 93 and negative 108. I can't remember what I'm just looking at here. That's supposed to say 1.93. Okay, so yes, there is all. That's the local minimum. The local maximum you find the same way, except for you choose maximum instead of minimum, and then you scroll over to that point. Once again, I think I will not do that, and I'll leave that for you to do. Okay, so we've just kind of run through all these things. Let's talk about some general descriptions of this function. As we said, it's cubic. We can say a couple of things about this. The domain of cubics, this is just true in general, is all real numbers. Unless, of course, this is a word, and if it's a word problem and the domain is restricted, that's another situation. But in general, as a math function, the domain is all real numbers, and the range is also all real numbers for all cubics. So that's nice. The one that we were looking at, let me pull it back up. It looks like this, right? So where is this increasing? Well, it's going to be increasing from here over and from here over. That's where it's increasing. And for the function, that's going to correspond to negative infinity up to the max, and from the max up to positive infinity. And it will decrease in the middle portion in here. The concavity, we actually have a change in concavity here. So we actually have an inflection point kind of like around here somewhere. And remember, an inflection point is where you change concavity. So that inflection point is somewhere in here. And on the left, it's concave down, and then it goes to concave up. Okay, let's ramp things up a bit and talk about a fourth degree polynomial. Basically the same questions. Not basically, exactly the same questions applied to a new function. So what does a fourth degree polynomial look like? Well, fourth degree polynomials kind of look like either this or this. That's not the greatest picture, but they're like M's or W's. Okay. So in terms of the maximum number of intercepts, you could have 1, 2, 3, 4. 4 would be the maximum number, and as far as local maximums and minimums, we could have 3 of them. 3 of them, whether it opens up or down. So once again, the process for this is pretty straightforward. It's just a matter of entering the function and then getting a decent graph, and then doing these same steps over and over and over again. Sorry. And make sure you don't screw anything up when you are entering the values. Just double checking it here. Okay, so I'm gonna do zoom standard again, except I accidentally pressed the wrong button, and I don't know what I just did, but it didn't give me a good graph. I did zoom square. So let's do zoom standard. Alright, so we saw 3 lines. There must be a 4th one, but just like in the last example, this is telling me that I need less x and more y. So -5. I'm going to try that and then do zoom fit. And once again, we have a radically different picture than we had before. I want to see, actually I said less x, but I actually want to see more x in the positive direction because I'm not seeing the whole function. So I'm going to go up to, I don't know, let's say 25 and just see what that looks like. That might have been too much. Okay, so that's actually pretty good. Let's actually do this. Let's go to 15 and then do zoom fit. I'm just basically roughly guesstimating where this function is, and now you can see I have way too much in the negative y direction, so I'm gonna reel that in. How about we just go to -500? Okay. All right, not fantastic. I need more than that, don't I? Sorry. Let's go to -2000. That might still not be enough. It's not. Anyway, the important thing, even though my picture is not perfect here, is that I can at least see what I was expecting to see, which is one of these 2 pictures, more like this first picture. Now, yeah, the hills are at different peaks, but the basic structure is the same. So now, I think I'll just do zoom fit with this picture that I have, and hopefully that will give me a better image. And it's not, it gives me a worse image. Yeah, I guess you can't win them all. Okay, so you can see that basically we just need to keep playing with this until we get a big enough window. Alright, next video we will finish this one up.